All right, section 3.3, we're going to be talking about graphs that are increasing and decreasing, or at least portions of where the graphs are increasing and decreasing. And we talked about this a little bit in section 3.2 when we talked about maximums and minimums. Do you remember doing those sine charts where we drew lines going up and lines going down based on the positives and negatives? That's exactly what this section's about, okay? So if you have your notes printed out, you're going to be super excited and helpful for that being helpful today because there's a lot written on them. If you don't, you get to write a lot today. Okay, so a graph is increasing by definition on an interval where when x1 is less than x2, f of x1 is less than f of x2. And a picture does a great job for talking about this. All it's saying on the number line is that if x1 comes before x2 on your x values, then the f of x1, the function value for at x1, is lower than the function value for x2. Maybe it looks something like that. That's all it means for the graph to be increasing, is that it's lower on the left than it is on the right. Decreasing feels a little bit awkward the way it gets worded, but it says an interval on which the function has the condition, x1 is less than x2, so we still have that the x1 value comes before the x2 value. But the condition that switches is that f of x1, that's the y value, is bigger than the y value on the second one. So the bigger y value comes first, and the smaller y value comes second. And that's what it means when we say something's decreasing. And we do it from sort of a visual perspective, right? We look at it and we just see that it's going downhill because we read graphs from left to right and so forth. But this is what it actually means in sort of in terms of inequalities. So what we're going to be doing is we're going to be using the derivative to make decisions. So Theorem 3.1 tells us, suppose that f is continuous on the interval I. If f prime of x is greater than 0, right, that means it's positive, then the graph is increasing. And if f prime of x is less than 0, that means it's negative, then the graph is decreasing. And we did this in the last section when we put these pluses and minuses in here, and I said, oh, look, plus means we're going up, minus means we're going down. It's the same thing we did in the last section. Positive is increasing, negative is decreasing. All right. Can I go to the next slide? This one's where there's going to be lots of writing. I told you. Theorem 3.2 is the first derivative test. Theorem 3.2 says the following. Suppose you have a function that's continuous on an interval, and you've got a point that's a critical number. Remember, critical numbers are found by taking the derivative, setting it equal to 0, or setting it equal to does not exist. So we've got a critical number. Then if we take the graph and it is positive, the derivative is positive, between A and C, the critical number, and then it's negative from C to B, then it means it's changing from increasing to decreasing, and we have a local maximum. We used this in the last section. I just didn't define it clearly. Right? We just sort of said it with our hands waving in the air and said, yeah, it works. Of course it does. Why not? And this is the graph where we had something that went from positive to negative. And I drew these sort of pictures like this and said positive, negative, and I said, look, maximum. That's what this says. Just in terms of the A's and C's of what you're seeing here, they're saying here is A, here is C, and here is B. So that's where the letters are falling in terms of their description. Okay. We could do the same picture on number 2, but it's flipped. This actually shows you that you have a negative first and then you have a positive second. So the picture is the same but flipped, right? It's negative and then positive. This is still A, C, B. And if it's negative, it means it's decreasing. If it's positive, it means it's increasing. And then, boom, there's a minimum. Yes?
So is this all just have to be like because it's the slope?
Exactly. You got it. It's all because it has to be the slope of the tangent line. And then it tells you some things about, and we saw one of these at the very end of class last time, and we flew through it lightning fast, so you may not have even picked up on it. This says that if you have the same sign, then it's not an extreme point. In the case where we did one, ours was an asymptote. So we didn't even have a value at that point. But you could have a graph where it is positive over something that actually exists. It's not an asymptote, but it's still not a relative extrema. So you might have something that looks like, so here's A, here's C, and here's B, and they're both positives. So in other words, the graph's going up and it's continuing to go up. And so yeah, there's not a maximum, there's not a minimum. I can't put that boom, that point in there. It doesn't work. And you've seen these graphs before. I'll just draw some parabolas to show you these. So if you had a parabola that looked like this, you'd have a maximum. If you had a parabola that looked like this, you'd have a minimum. And if you had something that wasn't a relative max or min, it might look something like the x cubed graph that we've drawn before, right? Where it's got a horizontal tangent line right here, but it's not a relative extrema. It's increasing on both sides of that point. Any questions on those so far? Okay, we're going to do some examples because that's what we do, right? Yeah, absolutely. All right, so let's see this, how it plays out in action. All right, so the first one we have is, or the directions say, find by hand all critical numbers. We've done that before. Use the first derivative test, which we've kind of done before too. But we're actually going to classify based on that then. Is it a local maximum, local minimum, or neither? So this sounds like something we've done before, doesn't it? Yeah, it does. It's just the directions are a little slightly different because we actually have the first derivative test cited here instead of not being cited from before. So let's take a look. Where did my page go? Here you go. All right, so we have our equation, f of x equals negative 2x squared plus 4x plus 3. What do we do to start with to find critical numbers? Take derivatives. Great. So somebody tell me, what do you get when you take the derivative of this? Be bold. You guys know it.
Negative 4x plus 4.
Thank you. Negative 4x plus 4. All right, so now Tristan's off the hook. Somebody else tell me, what do we do next? We solve for x, but we can't solve yet because we need to do one thing before we solve. Set it to equal 0, and then we'll solve, yeah. So we'll set this equal to 0. That's part of finding critical values. And then we solve it for x. What does this give me for x? 1. X is 1. Fabulous. So in section 3.2 and in the first derivative test, what does it have us do next? A sine chart, right? A sine chart. So we're going to draw a number line, basically, and we're going to put the critical point on the number line. We only have one critical point this time, so there's just one number on my number line. What did I do after I have the number or numbers on the number line? Test points. I need some test points. So I need a number before 1 and a number after 1. So somebody give me a point before 1. 0. Bless you all, 0. How about a number after 1? 2. That sounds good as well. All right. In a sine chart, I've got test points. Where do the test points get plugged in? In the derivative. You got it. So these points go into the derivative. So if I plug in f prime of 0 and f prime of 2, I want to know what I get, but I really don't care about the numerical value, right? Really just want to know positive, negative. So back into this derivative right here. If I plug in 0, do I get a positive or a negative? Positive. If I plug in 2, do I get a positive or a negative? I get a negative. All right, so this is where I like to draw pictures because I actually think very visually about descriptions like this. I like to draw my pictures. Positive means I'm going up. Negative means I'm going down. And that tells me something that happens right here. What can we say about this point at 1? It's a relative maximum. And your book uses the words local as well. Local, relative, they use them interchangeably, so you'll hear them say local sometimes. The directions say to classify each critical numbers, classify each location as a local max or local min, or neither. All right, so we found out that we have a local or relative, you can use that word. We have a local maximum at x equal 1. This direction said critical numbers. So x equals 1 is sufficient. If it had used the word critical points instead of numbers, we'd need to have an ordered pair x, y. So just as a reminder, what would we do if we needed to find the ordered pair instead of just the x value? Plug it into the original equation, right? And if you go back and do plug this into the original equation, it's actually 1, 5. Okay. So you don't have to write it if it doesn't ask, but sometimes they'll ask it that way instead. Yes?
Well, if we're asked to find an absolute maximum, will it always give us an interval?
Yes. Well, let me take a step back. It usually will give an interval. Occasionally it will give you a graph that you know it has a maximum, like a parabola, right? Like if you had a parabola that was opening downward, you don't really need an interval to give an absolute maximum. To give absolute minimum, you would, right?
Yeah.
But occasionally you'll see questions that are asked, and I'm thinking that there is one question where they ask you and they don't give you an interval, and they do it on a parabola. So you have to kind of use a little bit of your prior knowledge in there with parabolas on that particular one, but it's like one example or something of the whole set. So. All right, same directions, but the function is a little more interesting. Y equals x plus 4 over x. First thing we might want to do is to rewrite this in a more helpful way for taking derivatives. Something like this would be a good plan, right? You guys are familiar with doing that from your quizzes. So what do we do first to find critical points, critical numbers? Derivative, right? So we need y prime equals. All right, so what is the derivative of this function?
1 minus 4 to the negative
1 minus 4x to the negative 2. All right, now what do I do? There's a couple things I could do. Yeah, I need to set it equal to 0 for sure. In solving where this is equal to 0, what am I going to do?
You have to take the x back down and then
Yep, you're right. That's definitely one of our steps that I have to do. I need to consider this function kind of like it was originally given. You could move the 1 over. So I'll follow your lead since that's your suggestion. There's another way to do it we'll go back and look at. Is it negative 1? Does that work?
But that, it would have been 1 minus 4.
I changed a sign right here. Thank you.
Then, yeah, positive.
All right, does that look good? All right, actually it doesn't look very neat, but does it look like it's right? That's the important part. All right, now what? Okay, so something like this, 4 equals x squared. Then what? Okay, so what does x equal? Plus or minus 2. All right, so this is what happened when I looked for where the derivative is equal to 0. There is something else I have to take into consideration on this one that we didn't have happen on the other one. Does anybody know what it might be? Where that might have an asymptote, where the derivative doesn't exist. So if you take a look back here, right here, when we set it equal to 0, when we're dealing with polynomials, that's enough. Polynomials are never not existing. They're nice, smooth, they're easy to work with, they're convenient and clean. But anytime we deal with something where we've got like negative exponents, square roots, things get a little bit more creative, right? So we have the possibility right here that the 1 minus 4x to the negative 2 has a does not exist value. And in particular, you can actually see it pretty cleanly when you set it up like this. Where is this graph going to not exist? At 0, right? At x equal to 0. Does that make sense for everybody? So you do need to be aware of the kinds of graphs you're working with because you will lose something in the middle there if you're not careful. Because what we really have is we really have how many critical points? 3 of them, not just 2. All right, I'm going to take a step back and show you one other way that you could deal with it that's a little bit different. We still would set this x squared in the denominator, but so I'm going to erase, but just so that you can see another option, what we have here is perfectly fine as well. Okay, so I'm going to show you another way that you can think about this. What you could do is you could get a common denominator. In other words, this number 1 switches to x squared over x squared. So you have x squared minus 4 on top, and you have x squared on bottom. Clearly, that numerator, x squared minus 4, is where the 2 plus and minus 2 come from, right? You set that numerator equal to 0, x squared minus 4 equal to 0. So x is plus or minus 2. And then this piece right here is going to be the D and E part, going to be 0. Just a little different way of thinking about it. The solving of it is just a little different. Still get the same 3 critical points. So we need to test them now, right? I don't know if I've got space here left or not. I don't. So we will draw it. Just watch this. No problem. There's space right there. All right, we have 3 test points. I have 3 critical points. -2, 0, and 2. I need how many test points? Actually, I need 4 on this one, yeah. So somebody give me a number before -2. Okay, -3. Between -2 and 0? -1 sounds good. Between 0 and 2? And then after 2? 3. All right, so you're going to test these into which equation? The derivative equation, all right? That's the one that's actually boxed in purple, except for not the part that says equals 0. All right, so you're going to test them into here. All right, so one at a time, plug them in. Somebody tell me what happens, and I don't care what the number is, all I care is the sign. Do I get a positive or a negative when I plug in the -3 into the derivative? Be careful with your parentheses as you're plugging them in. This one's a little messier. Is it positive? Excellent. I've got 2 people that say positive. Now let's plug in -1. So I have 1 minus 4, -1 to the -2. Another positive, huh? I have negative written down. Can we double check on that one? You got a negative? Double check the value in yours, Christian. Okay, let's test number 1. What if I plug in the number 1? Another negative. Okay. And the value at 3? Positive. And in some sense, it should make sense that I'm getting the same thing at -3 as I do at +3 and -1 as I do at +1, because when I'm plugging them in, I'm really plugging them into an x squared location, right? So when I square it, it doesn't matter whether it was positive or negative to begin with. So that seems to make sense. All right, so I'm going to draw these sort of pictures in here now. Positive means I go uphill. Negative is down. Then positive is back up. So what happens at -2? We have a maximum. What happens at 0? There's actually an asymptote. At the very least, from this sine chart, we know we have neither, right? What happens at 2? This is my minimum. So we have a local maximum at x equal to -2. And if you were asked for the ordered pair, you could put the -2 back in the original equation, and you would find that it's -2, -4, just so you know. And then there's a local minimum at x equal to +2. And again, if I plugged that in, I would actually end up getting 2, 4. Again, it doesn't ask me for that on this particular question, but some of the questions you're posed with will. Any questions on that one? Okay, we're going to do at least one more question here. So I've got a few minutes left. Directions are different on this one. They wanted us to find all asymptotes. We know how to do that, right? By hand. We've talked about this before. And then it also wants us to find the extrema. Okay, that's max and mins. And then sketch a graph. Well, sketching the graph's a little bit trickier. That's not something we've actually done with these just yet. All right. The asymptotes, we did that back in chapter 1, I think, right? It's been like a month at this point, I'd suspect. There's 2 types, or there's 3 types of asymptotes. Can somebody tell me what one of them is? vertical. Another one's horizontal, and the third one, slant. Good. Can you tell me which kinds this graph's going to have? Definitely going to have vertical. How do you know? Surprise, two-part question, right? How do you know? Because it has a denominator that could be 0, right? Yeah, if the denominator has the ability to equal 0, it's going to have a vertical asymptote. What else do I have? Horizontal or slant? Which one? You get one or the other. You can't have both. Slant? Why? You can divide the top by the bottom, but that's not what it means for it to be a slant. It has to do with the degree. What does the degree tell us? They're the same, right? Do you remember slant asymptotes, the degree of the top has to be 1 bigger than the bottom. Now, we do have one of the cases of the horizontals that are a little bit different because the top and bottom degrees are the same. So let's actually start with the horizontal asymptote since that's sort of where we're stuck at this point thinking about. Do you remember the case that this is? I've got the degree on the top and the degree on the bottom the same, so what do? I use the coefficients, right? What is the coefficient of the highest degree on top? It's a 1. What's the coefficient of the highest degree on bottom?
1.
It's also a 1. So now don't you dare tell me the horizontal asymptote is 1. You guys lost points. Most of you did, actually, I think. Do you remember what you have to do? X or Y? It's Y. It's Y equals 1. Horizontal lines are Y equals. Vertical lines are X equals. Okay. So we've got a horizontal asymptote at Y equal 1. That's good information. All right, so Matt had told us before we even got to this point that we were going to have some vertical asymptotes. And Edgar mentioned it had to do with the denominator, or maybe Christian, one of them mentioned the denominator equaling 0, right? So we're going to take that denominator and we're going to figure out where exactly it does, in fact, equal 0. So when you have a function like this, x squared minus 4x plus 3, what do I do to find out where that is equal to 0? Factor if we can, or quadratic formula if we can't. This one's pretty and nice enough that it actually factors. So somebody help me out. What does this factor into? X minus 3 and x minus 1. Good. So what does x equal? 3 and 1. And those are 2 of my asymptotes now, the 2 vertical ones that I have. And I'm not going to have a slant one. So the first directions, which said find all asymptotes by hand, we did that. So, we can check that off the to-do list. Next thing is extrema. How do you find extrema? You do derivatives, right? Absolutely. Of this. Oh, because what's that going to mean? Quotient rule. Yes, it is. And some beautiful foiling things out when we're done, I'm quite sure. All right, so somebody help me. Taking the derivative. What do we have? Denominator. So that's x squared minus 4x plus 3. And then what? Derivative of the top, which is 2x. Excellent. Then what? Minus. Okay? Okay, so you took the derivative of the denominator. Next, is that what you did? Okay, the derivative of the denominator, so the 2x minus 4, good. And then times the x squared, the top, right. Oops, I left my squared off. Now, some of you like to stop here. That's right. But you have to remember to divide by what? Do you remember, Raven? Yeah, the denominator squared. We need to simplify that numerator. It could have been worse, I promise. We don't end up with any, like multiplying 3 things by 2 things or anything like that. So that's at least nice. All right, so I have x squared times 2x, so that's 2x cubed. Negative 4x times 2x, which would be negative 8x squared. And then 3 times 2x, so 6x. And then I have to have a negative on what I'm doing here, but I need to 2x times the x squared, which would be 2x cubed, but negative, because there's a negative in front. And then I need this negative 4 times the x squared, which is negative 4x squared, but then there's another negative, so it's positive 4x squared. And all of this is over x squared minus 4x. Oops. plus 3 quantity squared. Somebody tell me something nice that just happened.
The 2x cubed.
Don't minimize how nice that is. That's a very nice feature. The 2x cubes just canceled out. And some of the other pieces still combine, right?
Yeah.
Okay, so what do I have? Negative 4x squared plus 6x. Okay, so this is my reduced expression for my derivative now. And we might have lost track of why we were doing the derivative. I hope not. Do you remember why we were doing the derivative? To find the extrema. So once I do a derivative, what do I do with it? Set it equal to 0. Right. Now, this value is kind of like the last one where I showed you, hey, look, we could have a numerator equal to 0, denominator equal to 0, and that's exactly what we're going to have here. We're going to have critical points at every location where either the numerator equals to 0 or the denominator equals to 0. And we know where the denominator equals to 0. Where does the denominator equal to 0? We did it once. We already did it on the screen. 3 and 1. Right here. These two places where I have vertical asymptotes is the same place where the denominator was equal to 0. So those are going to be on my sine chart. The 3 and the 1 are for sure. We also had to figure out where the numerator is equal to 0, which we haven't done that part yet. So my numerator, negative 4x squared minus 6x equals to 0. What would we do? Factor out a negative, and I can even do a negative, right? Negative 2x. So what's that going to give me? 2x plus 3, good. And that's going to give me two values, right? Somebody already told me x equals 0 is one of them, the first piece. From the second piece, what does x equal? Right. So how many critical numbers do I have? 4. Do you have a question? Yes, I have a sign missing. Thank you. Sorry, my screen doesn't show the whole screen at once like you guys can see it. So I have positive 3/2. Does that look better? All right, so there's 4 critical values, right? So I have critical numbers are x equals, I already had 3 and 1 from my vertical asymptotes, and then now I also have 0 and 3/2. Let's do this portion of this, and then we'll stop. Let's just do the sine chart real quick, okay? So on my sine chart, I've got these 4 values, which means I have 5 test points. Oh, the smallest one's 0. Then I have 1, 3/2, and 3. And we're going to pick test points in between there. And I know you guys know how to do this. We've done this several times now. So let me just show you what happens. Would that be okay? All right. At the first one, we get a positive. The second one is also a positive. The third one's a negative. The fourth one's a negative. And the fifth one's a negative. That's what it will end up happening. So positive, positive, negative, negative, negative. What can you tell me about relative extrema from this sine chart? There's only one. That's one of them. And it's a maximum. So I don't really have enough space to write it in here, but I'm going to pretend like I do. I have a local max at x equal 1. Okay, so far, the pieces of information I'll need to graph, and we'll do it next time, is I have a horizontal asymptote at y equal 1. I have 2 vertical asymptotes at x equal 3 and 1. And then I already have my local max boxed in over here at x equals 1.
I'm already doing this one, but when you plug it back into the original equation, don't you get a 0 in the denominator?
Do you get a 0 in the denominator?
1 minus 4.
At x equal 1? You do. Maybe I have my signs wrong. We'll fix them next time if I do. That's okay. No worries. If that's the case, maybe I have a sign written down wrong because I was doing it really quickly. We'll see. We'll check it next time. All right? No worries.